Hello, I'm Professor Steve Miller. Today we're going to look at the turbulent kinetic energy equation and its derivation. Let's recall that turbulent kinetic energy will be called K, and we'll say that is equal to 1/2 of u prime I bar, which is the trace of the Reynolds stress to the half power, which we can expand out as 1/2 of u prime squared plus v prime squared plus w prime squared. No problem. And we'll do that by looking back at equation 16, and I'll write 16 again just to remind you what it is. We derived it in the previous lecture. And it's uk partial xk of ui uj prime bar, which is equal to dij plus pij plus phi minus epsilon ij. And we defined these terms here, of course, in the previous lecture too. So review that if you don't recall what they are. We'll set I equals to j, and that way you can see we'll recover k in this particular term, which we just defined up here. So let's do that. And we'll find u sub k of partial xk equals d plus pk minus epsilon. And you'll notice that I've dropped the subscripts here because, of course, I equals j. And we'll call this equation 17 in the course lecture notes. Now let's define d, p, k, and epsilon with I equals j. d will be equal to partial xk of kinematic viscosity of partial xk minus 1/2 of the triple correlation over bar the whole thing minus 1 over rho of p prime uk prime in parentheses. So that's d. pk will be equal to negative ui uk prime bar of partial ui partial xk, and epsilon will be equal to nu times partial ui partial xj partial ui partial xj prime bar. So we have our dissipation term. Now you'll note that Vij contributions vanish. Why? Well, these terms serve to redistribute the energy among the different components of Vii. Let's look at Vii of Vij, which is 2 over rho, which is the density of p prime partial ui prime partial xi bar is equal to 0. Why? If you look back in your notes at equation 9, you'll see that's actually the continuity equation or conservation of mass. And so this term, indeed, will be going to 0. So that's really our major equation for turbulent kinetic energy. K, and right here, of course, is we have our very important equation which we'll use throughout the class, number 16 originally, setting I to j, and finding turbulent kinetic energy equation, which we'll call TKE equation. Very important equation, and of course it's foundational in all K epsilon type or K omega models, the most famous two equation models, which we'll talk about later in the course. Now let's consider two-dimensional flows. Why? Well, of course, they have applications to boundary layers. And we have other videos and lectures online about what boundary layers are. So, if we are two-dimensional, and after time averaging, we'll see, of course, that u3 equals 0. That's the w component of velocity is 0. There's no flow in the span-wise direction or into the page. Also, u1 prime, u3 prime bar is 0. And also U2 prime, U3 prime bar is 0. Why? Because of course U3 prime with its correlations will be 0. Okay. We'll also know that all derivatives with respect to x3 are 0 for all time averaged quantities. Under these assumptions of two-dimensional flow, our equation 17, with these assumptions, will become u prime, or u1, excuse me, of partial k partial x1 plus u2 partial k partial x2 equals d plus pk minus epsilon. And of course here k is nothing but 1/2 the trace of the Reynolds stress tensor, which we defined way up here. I'm going to have to refer to these assumptions again. I'll say these are 18. So for 19, this is equation 19, and I'll make these same assumptions to d and pk now. So what will d? Let's write d out. It's quite a big equation, so let's get ready. D equals nu partial 2k partial x1 squared plus nu partial 2k partial x2 squared minus partial x1 of 1/2 of u1 prime times u1 prime plus u2 prime squared plus u3 prime squared. This is squared too, it's a prime. In parentheses, all averaged, minus partial x2 of 1/2 of u2 prime, u1 prime, u prime plus u3 prime squared, all averaged in parentheses, minus 1 over rho of partial x1 of p prime u1 prime bar minus 1 over rho of partial x2 of p prime u2 prime bar. And you notice, of course, there's no partial x3. So that's d. pk for the two-dimensional flow would be negative u1 prime squared bar partial u1 partial x1 minus u1 u2 prime bar partial u1 partial x2 minus u1 u2 prime bar partial u2 partial x1, and you can guess the last term, u2 prime squared partial u2 partial x2. So you see we just iterated over 1, 1, 2, 2, 1, and 2, 2. All the 3's are dropped. Next, let's do the dissipation, and we'll just divide the whole equation by kinematic viscosity. So we'll have epsilon over nu is equal to u1 prime over ux1 squared bar plus u1 prime partial x2 squared bar plus partial u1 partial x3 prime squared bar plus partial u2 prime partial x1 squared bar plus partial u2 prime partial x2 squared bar plus partial u prime 2 partial x3 squared bar plus partial u3 prime partial x1 squared bar plus partial u3 prime partial x2 squared bar. And one more term, if you've been watching, you can figure out the pattern. Partial u3 partial x3 prime squared bar. Wow, so that's it. Now, that's the two-dimensional assumption for turbulent kinetic energy equation. Now let's make another assumption. Let's assume that we have a boundary layer, which I'll just abbreviate as BL flow. what do we have then? Partial of partial x2 is much greater than partial of partial x1, right? That means the derivatives in the y direction, or the direction in the cross-stream direction away from the flow, are much greater than the streamwise direction. And u2 is much, much smaller than u1. That is, v is much, much smaller than u. So the boundary layer, remember, is like on a plate. And there's some boundary layer profile. It looks like this. And you can see u is much bigger than v. And of course, the change in the profile changes very little in the x1 or x direction. And of course, this is the y or x2 direction. So that's what our assumptions are for TKE equation, K equation, in the boundary layer. So now equation 19 with these assumptions will be reduced to u of partial k partial x plus v partial k partial y is all equal to d plus pk minus epsilon. And what are these two quantities? Well, what is d? And we'll call this equation 20. D will be partial y of nu partial k partial y minus 1 over rho p prime v prime bar minus 1/2 of v prime quantity u prime squared plus v prime squared plus w prime squared bar, just like that. And then we just have pk left. That will be negative u prime v prime bar partial u partial y. Everything else is gone, which is nice. Okay, we can now substitute, remember, u1, that is in this notation, we've substituted already, excuse me, u1 equals u, u2 equals v, x1 equals x, and x2 equals y. And we've introduced this in almost the first class. So this is the famous equation number 20, indeed right here, for the boundary layer turbulent kinetic energy. And what are the properties of this equation? In fact, number 20 has certain properties. Let's just make some notes about those. First of all, it's a convection diffusion equation. And if you look on Google, you'll see there's many properties of convection diffusion equations, which is wonderful. And it has a particular source or sink. Now the turbulent kinetic energy, which I'll write as TKE, turbulent kinetic energy, is convected by the velocity vector u equals u I plus Vj through the advection term, which is the left-hand side. So advection term, if you look at equation 20, is really left-hand side, and that's u of partial k partial x plus v of partial k partial y. Great. Here's another note. We'll say that the TKE, turbulent kinetic energy, that's K, mind you, is diffused by D. It's the diffusion term. And it consists of molecular diffusion, pressure diffusion, and turbulent diffusion. Another note, turbulent kinetic energy, or K, is generated should be is by the production term P, which is right here, which extracts energy from the mean gradients of the velocity field. Mean gradients of the velocity field. So let's look at production. See, production has something to do with the Reynolds stress, the off-diagonal term, U1, U2, primed bar, times partial U, partial Y, which is the derivative of the velocity, the mean velocity, with respect to Y, the direction away from the wall. And that's where, of course, turbulence comes from in this particular turbulent kinetic energy budget. One final point. The TKE, or turbulent kinetic energy K, is dissipated into heat only, because this is an incompressible equation, as a sink in epsilon, which is the so-called turbulent dissipation rate. With these particular thoughts, go back and look at the boundary layer TKE equation, equation 20, and the general turbulent kinetic energy budget for, indeed, incompressible flow, equation 17. Thank you very much. I'm Professor Steve Miller.